Good afternoon, everyone. I'm Vinodhkumar, an MSc student in Sustainable Energy Systems at the university. So I'm going to explain my undergraduate program in the country. So my undergraduate program was on control of grid-connected hybrid energy system using synchronous reference frame technique. So a quick overview. So this project combines three renewable sources of solar, fuel cell, and a battery, and its interconnection with the grid using the synchronous frame reference technique for the control technology. Some introduction. So nowadays the electrical system is experiencing increased load demand. It also has limited power delivering capability, and there's always time delay in building new infrastructure, be it power plants, transmission, and distribution lines. So one of the solutions is to go for distribution generation. DG means generating at the site where the load demand is based on. So DGs can vary in size from 5 kilowatt to 30 plus megawatt. The efficiency, the maintenance, and the emission depends on the type of technology you use. So we look at the different generation technology. DG need not be renewable as such. It can be a diesel generator which you can use as backup power if the power supply fails, or it can be pure renewable devices like photovoltaic or wind turbine, or storage devices like batteries and fuel cells. Moving on. So hybrid energy system. Why go for an hybrid energy system? Well, in a standalone system, like for example, if you take a PV system, its power generation is intermittent. It depends on the weather conditions. So whereas in an hybrid system, you could combine a different source and still get continuity of supply with it. So, and yeah, so the hybrid energy system can address limitations such as the flexibility, and it's reliable, the emissions if the sources are fully renewable, and it's economical. The currently studied hybrid systems are PV diesel, PV wind diesel, wind diesel hybrid systems. So I've gone with PV, battery, and a fuel cell hybrid system. Why I've gone with this is like the PV system is already widely used in domestic applications and industrial applications. So, but during night time we won't get any supply unless we have stored energy. So combining a PV with the fuel cell, you'll get a fast and reliable backup. But there is a problem with the fuel cell too. It can be slow due to its operational processes. So a third addition would be a lead acid battery, which can be used for step load changes. All the renewables generate DC supply, which can't be directly interfaced with an AC grid, so you need conversion. And if uncontrolled interconnection is made with the grid, you will experience voltage oscillation and protection issues. So yeah, so using an inverter is highly efficient and reliable. It's low cost and there is no transformer use as such. And commonly used is a current control voltage source inverter to interact the active and reactive power flows of the grid. So the inverter control approach, there are three main approaches, namely synchronous, stationary, and natural reference frame. So each use their own transformation, like synchronous uses an ABC to DQ transformation and ABC to alpha beta. For those who may not know, these transformations are used for analysis in electrical machines. So once the I've used synchronous reference frame technique for this. So once the transformation from ABC to DQ is confirmed, the control variables we want. So for example, when you convert the voltage, they'll become DC quantities, and So with these quantities, you can easily control the output. So you can use a PV controller to easily compare the reference value with the grid values and do calculation. So and synchronous frame is simple and most extensively used. The disadvantage being is that it does need a precise grid synchronization. So as I said, synchronous reference frame technique uses path transformation, which is conversion of ABC to DQ0. So in a balanced three-phase system, you'll get only DQ. The zero component will be 0. So this is the transformation matrix that can be used to obtain transformation, and the theta is obtained using PLL technique. Theta is the phase angle which is needed for the transformation. So power control. With synchronous reference frame technique, it's easy to control the active and the reactive power flow. So once we have aligned, the reference frames and made PQ is equal to 0, the active power flow can be represented by this equation, and the reactive power flow using this equation. So we will get the ID and IQ values from the grid, and we can set reference values based on our demand, and we can control the power exchange between the grid and the inverter. So this is the system that I use. So it's got the 3 sources which is connected to the grid via the 3-phase inverter, a filter circuit to filter out the harmonics, and this is the grid part. So we take voltage readings of the filter for the PLL block to obtain the phase angle, and then we obtain the grid current values here. So we can set the IQ reference and ID reference as we please, so that we can set the required active and reactive power flows. So there are certain standards which need to be followed when we connect a renewable with the grid. So these are set out by the IEEE 5147/2003 and the IEC 61727. So these are the standard. I have designed a 5 kilowatt system. So I've just tried to maintain the total harmonic distortion to 5% in my simulations. So going to the simulation system. So I've modeled a PV module for total output capacity of 2 kilowatt. I've used the MATLAB Simulink block of and metal hydride battery and a fuel cell. It's already available in MATLAB, so I didn't model that. So this is the model of the PV. So each block is the representative of each component in this equation. So this is a PV module, and I've combined 5 to get a 2 kilowatt output. So I've used the standard test conditions of 1000 radiation and 25 temperature, and the details that I've used are the SPR305 module. So this is a Simulink model of the entire system. So we have connected 5 fuel cells, a battery and a fuel cell. So they both will generate a load capacity output voltage of 750 watts, and the output voltage will be the output voltage will be 750 watt and the output power will be about around 5 kilowatt. So this is the entire Simulink block diagram. So that's the hybrid hybrid system, the inverter, the filter circuit, the grid, and it's the grid control. So I've connected this at a common bus, and these are the free loads that I've used. So moving to the SR technique. So this is the power that is being supplied by the grid. This is the power that's needed by the load, and this is the power that is supplied by the inverter. So we calculate the difference, and that will give us the ID reference value. And I've set the IQ reference to 0, so the system won't supply any reactive power. So we calculate the difference between the reference value and the demand value, and we give it, and we generate the modulation index for the PWM generator. And so the PWM generator generates the pulse signals for the 6 switching devices. So this is the inverter phase voltage filtering, before filtering and after filtering the inverter phase voltage. So it will be line voltage, this is phase voltage. So these are the reference power values I've taken. So for between 0 to 0.2 seconds, the demand will be 1000 watts, and after that increase to 4000 watts, and a reference and a reactive power reference of 1000 watts, and after 9002. So this is the system operation. So since the hybrid system has a capacity of 5 kilowatt, for the initial load demand till 0.02, it is supplied, the entire power is supplied by the hybrid system, and the grid doesn't supply anything. So after 0.2 to 0.3, when the demand goes to 4000, the real power is supplied by the hybrid system. And since I've set the hybrid system not to supply any reactive power, it will be 0 the entire duration, and any reactive power demand that's needed is supplied by the grid. And so you can see the total load part here. These are the current values. So as I try to set the interconnection with the grid, has to, the total harmonic distortion has to be maintained less than 5%. So try to maintain it low, and for this cycle it's 1.63%. So in conclusions, the PV fuel and battery was found to provide a continuous supply. The DC transformation, since the control variables are DC, the control and filtering is achieved relatively simpler. And the main advantage is, like, you can control the amount of power that you give to the grid. So it's I've done a very simple simulation, so I like to develop further models of it, and the long term would be to develop an accurate model of DG and fully understand its behavior. I've not done any source side control of it. Like for solar panels, I have not used any MPPT techniques as such, so I would like to do that. And when interconnecting with the grid, island detection is one of the main things, but I've not incorporated that in my simulation. Thank you.
Okay, thanks for another interesting overview. We got a very keen judge here to ask a question on this, so on universities.
keen. I was just very quick to raise my hand. Anyway, so thanks for the presentation. It was very nice. I have one comment and then one question.
Okay.
First of all, I'm a bit uncomfortable about the fact that you connected all your sources in parallel without any individual converter control.
Okay.
Because obviously each of those three different sources will have different needs in terms of control. They will be different in size. So if you have a fuel cell and a battery connected in parallel and the battery is much smaller than the fuel cell,
Okay.
the battery will be depleted before the fuel cell does. And then you will need to, I mean, I guess for a small experiment or simulation is okay, but in a real system,
Yes. Yeah.
that wouldn't work. My question was about the fact that you said that your three sources, the PV, the fuel cell, and the batteries, supplied continuously power to the load. What you didn't show was the size of the load and if it has any particular profile or if it's constant. So you said you managed to have your sources supply the load, but you didn't say what's the relationship between the two. So how easy or how difficult was that in any case?
The load variance with time, you mean?
Yes.
No, I assume the step change in load, a constant load profile for.
Okay. I don't understand what the objective was then. Was the objective to make sure that your voltage is and frequency are constant? Was it to make sure that you have enough capacity to support the load?
It was just enough capacity. For example, if the load was 1000 watt, and if it could supply 1000 watt for that duration.
Okay.
And I think you should also take the blue line is reactive power here.
Yes, I did mention that. Sorry.
Because
Yeah.
you're actually
Yeah.
giving only pure power.
Yeah.
Any other questions, John?
You had a similar model of the fuel cells. Can you go back to that figure?
Yeah.
Yeah, that's okay. So you've got the fuel cells, the battery, and the PV array, and then they all connect together.
That's a summer. That's a summing block in MATLAB.
Right. Okay.
Okay. Yeah.
But what you've done there is you've measured the voltage from the fuel cells
Mm.
and the voltage from the batteries, and then you've put that into what looks like a sort of multiplexer.
This one?
Yeah.
That's a summer.
Okay.
Yeah.
So that sums the output from each of the different sources,
Yes.
and then you recreate the voltage source after that.
No, that's for connection with the inverter. So this is sorry. So these blocks are taken from the Simulink power systems toolbar. So they won't connect with the normal signals. So I had to use this block to provide
Okay.
connection points for the
Okay.
inverter.
So you had to convert the electrical output from each of the sources into signals.
Signal.
and
So
then-
these are signals. Sorry, these are
Okay.
signals. So I have to convert them to electrical.
And then you convert them back into electrical.
Yes.
Okay. Was there any reason for doing that?
I have to interconnect with these switches there.
Okay.
You know,
How would you do that in reality?
in real.
Well, in reality, you wouldn't have a summing block, would you? You would have the output from each of the sources,
Yes.
and they would be electrical. So, how would you do that in a physical system?
Assume, if I may add, that at some point you would
Okay.
like to charge this charge button.
Mm.
So your flow may not go via converter or may go from the grid
Okay.
and converter to the battery.
Do you have a short answer for this?
I've not done any sided, as I said, any source side control as such. So
If I may add, I mean, it's actually proof of concept that something could be done and simulated with
Yeah.
no longer work in meters. We understand.
Okay.
We all have problems going from modelling to real life. So I think that's probably a good message to end that.
Thanks.
Thanks again.
This production is brought to you by the University of Edinburgh.